Okay, physical science, welcome back. We're going to finish up section 2 using a scientific approach today. But before we do that, I'm going to give you a quick little recap. If you remember from the end of the first video here for section 2, we were talking about how a scientific theory is developed, how after multiple experiments, we get the same results over and over again. We can call it a theory. We know kind of how things are going to operate. So it's kind of a statement to say that yes, we have tested this and it has occurred enough that we can say that this is definite enough to get the title of theory. So now we are going to talk about how something that is a scientific law is different from those theories, so that they might kind of sound similar and they might get used interchangeably. However, they are very different actually. So how they differ is that after repeated observations or experiments, the scientists may arrive at a law. Which again, that sounds kind of similar to theory, but again, as we go on here, we're going to start to see some definite differences between the two. So a law, which I would definitely write this down, is a statement that summarizes a pattern found in nature. And these are going to be really important in physical science because non-living things definitely follow patterns. There's not a lot of brain activity in non-living things to kind of help them go against the patterns that are set. Like again, in nature, sometimes in biology, there's always seems like there's exceptions to rules. When we come to a law, talking about physical science, those usually do not occur. So the example we give is Newton's law of gravity is a scientific law that has been verified over and over. Scientists have yet to agree, however, on a theory that explains how gravity works. So we know that if we take our pencils and we drop them on the ground, or hold them up in the air and drop them, that they're going to fall to the ground. That is a law. It has been verified on Earth in normal situations. We've never had someone drop a pencil and it goes shooting back up into the ceiling and gets stuck. That has absolutely never happened, so that is why we can call the law of gravity a law. However, if you notice, we have yet to agree on a theory that explains how gravity works. So we really don't know the mechanics of exactly what is causing those things to fall. We just know that it does happen. So that is kind of one of the differences of how a theory and a law can be different from one another. And then again, we're going to keep going here. And then again, another definition of our law. It describes the observed pattern in nature without attempting to explain it. So the explanation of such a pattern is provided by a theory. So this is a really important point here about the difference between the two. So the law just simply describes an observed pattern in nature. So we see that every time we drop our pencil onto the ground, it falls. We call that the law of gravity. However, we do not have an explanation of why that pattern is occurring. Why has this pattern occurred? Are there magical little forces somewhere pushing it down? Again, that's obviously not the truth, but again, that is how the theory and the law differ from one another, is that one, again, the law just tells us, again, this is what happens. The explanation would have to come from the theory, which we don't always have. So to finish up here, looks like we're going to talk about a model that that will actually help us as another concept that will help us in when we talk about the scientific approach. So a model is a representation of an object or event. So anything that can represent something else. So the example they give us here is that a street map is a model of a city. So the city is obviously too big for us to hold in the palm of our hands to look at and how to get around. So we have a map that shows us how to do that. So if we look right here, scientific models make it easier to understand things that might be too difficult to observe directly. Again, now maybe a better analogy for this is maybe the maps. The Google Maps app on your iPhone is a model of the city or the place that you're trying to get to. Again, it's hard for us can't just fly up and look down at all the roads and see what's going on. We actually have to have a model that helps us out with that. And if we look down here at our example, we have this computer model represents the interior of an airplane. It helps engineers visualize the layout of the plane. Again, planes are gigantic, so we're not going to be able just to easily, and obviously planes aren't transparent, so we're obviously not going to be able to easily see the inside of a plane. So they've generated this computer program, this model, to help them kind of scale down the plane a little bit to make it easier to figure out how it is laid out and maybe how they can work on it. However, models can also work the other way because they can help us visualize things that are too small to see, such as an atom, or things that are large, again, such as the solar system. And again, we're going to hopefully work with models where maybe we build some atoms this year and maybe make, again, some smaller scale models of some bigger concepts. And then there's also an example of mental model that's rather than a physical, and that just is maybe something like a little trick that can help you remember something. And the example that they give is that comets are like a giant snowball, which is primarily made of ice. So you might not have known that, but anytime you see, again, you hear about something called Halley's Comet, which only shows up every so often years. It just burns really bright in the sky, and that actually is basically a giant snowball. It's because it's made up of mainly ice and dust up there, kind of zooming around at high speeds. And as new data is collected, models can be changed or replaced by new models. So that's a big thing in science. It is always changing. There's really never one set answer here. And to finish off, the scientific approach is actually working safely in science, which hopefully we went over this on the first day, so hopefully this isn't anything too new. And it is saying that just safety plays an important role in science. Lab work may involve flames or hot plates, electricity, chemicals, hot liquids, sharp instruments, and breakable glassware, which again we went over all of that on the maybe it's actually the second day with our safety contract. And as this stuff comes up in the lab, we'll hit on it more in depth. But make sure as we get into this stuff, you're always following my instructions, and if we're working out of the book or a lab manual of any kind, make sure you follow those directions and don't kind of go rogue and go off on your own. So that is it for section 2. Let me know if you have any questions.